Look up at the board here. We see two pictures. One of a hockey team, the Washington Capitals, who, by the way, before the All-Star break this year, have gone 35-8-4. That's 35 wins, 8 losses, and then 4 overtime losses. And we see a picture of a train. What do the Washington Capitals, pains me to use the Washington Capitals as an example for this because I don't like the Washington Capitals, but nevertheless, what do the Washington Capitals and the train that you see up on the board right now have in common? Carrie? Wow, good answer. That's exactly the answer I was looking for. Almost like I gave you the answer ahead of time. They're hard to stop, right? If you're 30, look, you've won 35 games. You've lost 8 games. It's hard to stop the Washington Capitals. It is. It pains me to say that because I don't like them. The only team I like less than the Washington Capitals might be the Red Wings. No, I actually don't mind the Red Wings. They're difficult to stop, whether I like them or not. This train is difficult to stop as well. But it's 2 different ways of being difficult to stop, right? Right? Psychologically, it's hard to stop a good hockey team or a good football team or a good baseball team or whatever. It's physically difficult to stop a train. What's the term that we sometimes associate with a train that's difficult to stop, or for that matter, a hockey team that's difficult to stop? They both have a lot of, that's a term that we're going to talk about in just a second. You mentioned it earlier on, though, the one that I want here. They both have a lot of momentum. Yeah. Who's got all the momentum in the NHL right now? The Washington Capitals do, because they've won 35, they've won 27 more games than they've lost in regulation time. This train also has a lot of momentum. This is the kind of momentum that we're going to focus on in this unit, obviously, because it's not psychology class, it's physics class. We both start with the same letter, but how difficult is it to stop something physically, not how difficult is it to stop something psychologically. In fact, that's the way that we're going to define momentum, at least in an everyday usage kind of thing, how difficult it is to stop something. That's not the real definition, but it's how we're going to think of momentum. The real definition is the product of an object's mass and velocity. Think about that for a second. What makes something difficult to stop? Physically, that is. Not the hockey team. We're talking about the train. What makes a train difficult to stop? There's 2 things. 2 factors. What's one, Nick? It's mass, yeah. The heavier it is, the harder it is to stop, right? If you got a train moving down the track at a certain speed, and you got a bicycle moving down the road at the same speed as the train is harder to stop than the bike is. The train has more momentum. It's harder to stop. It has more momentum because it weighs more. What's the other thing that affects the amount of momentum something has? What's the other thing that makes something harder to stop? Yep. No, let's look at the properties of the object itself only. So the answer there, by the way, if you didn't hear it, was the force of friction or a reverse force of friction. We're not looking at external factors right now. We're looking at fundamentally the properties of this train or this bicycle or whatever it is, this baseball or this hockey puck or whatever it is. What makes that puck, what makes that train, what makes that bicycle hard to stop? Fundamentally, properties of that object, not outside factors like friction. Speed or velocity, right. The heavier something is, the harder it is to stop. The faster something's moving, the harder it is to stop. Look, when my 4-year-old is riding a little bike with training wheels, I can step in front of that bike and I can stop that bike. When my 13-year-old is riding his bike, I'm not going to step in front of that bike and try to stop it. Why? Well, he weighs more, but that's not the big factor there. My 13-year-old rides his bike much faster than my 4-year-old rides his bike. It's a lot harder to stop the bike that's moving faster than it is to stop the bike that's moving slower. So 2 things affect how hard it is to stop something: mass and velocity. Therefore, the real definition of momentum, although we think of it as how hard it is to stop something, the real definition is the product of mass and velocity, because that's what makes it hard to stop something. Now, you mentioned a term, Carrie, a minute ago, inertia. We're going to compare that term with inertia right now, momentum with inertia. They're real close. Some people get the two mixed up. Some people just kind of assume they're the same thing. In fact, for a lot of uses, you can kind of think of them the same, but they're not quite the same thing. Momentum is how hard it is to stop something. Inertia, listen carefully to the difference here. Inertia is essentially how hard it is to change the motion of something. What's the difference? How hard it is to stop something, how hard it is to change motion. In other words, remember in physics 20, the tendency to maintain its current state of motion, the tendency to resist a change in motion. What's different about those? What's different about inertia and momentum? Let's look at two trains here. The first one, again, that's moving down the tracks. The second one this time is sitting in a station. Let's look at the first one. Is this train that's moving down the tracks hard to stop? Yes, so it has momentum, right? Is this train that's moving down the tracks, is it difficult to change the motion? Is it difficult to cause it to speed up or slow down? Sure, it's heavy, right? So it's got momentum and it's got inertia. What about this train that's sitting in the station? Does it have momentum? Is it hard to stop this train that's sitting in the station? It's already stopped. It's in the station, right? It's not moving. It has no momentum. So this one has momentum. This one has inertia. This one doesn't have momentum. Does it have inertia? Is it difficult to change the motion of this train that's sitting in the station? Yeah. You ever tried to push a train and get it moving? I mean, I use that kind of rhetorically because I haven't done that either. But I assume if you did try to push a train and get it moving, you'd probably have a pretty tough time with it. It's difficult to change the motion of this train, but it's not difficult to stop it because it's already stopped. Momentum is how hard it is to stop something. Inertia is just how hard it is to change the motion. We'll say it's the tendency to keep its current motion. The tendency of an object to keep its current motion. This train has a lot of momentum because it's got mass and velocity. This train doesn't have momentum, although it's got mass, it doesn't have velocity. This train has a lot of inertia. Why? Not because it's moving, because it's got mass. It's got a lot of mass. It's hard to change the motion of that train. This train also has a lot of inertia because it's got mass. It's hard to change the motion of that train. Which one has more inertia? Which one has more momentum? The first one. Which one has more inertia? Probably about the same, because they're both heavy trains, right? Momentum depends upon mass and velocity. Inertia depends only on, what's the word I want to write down here? One word. Yep. Mass, just mass. So it doesn't matter how fast it's moving, it's its mass that determines how hard it is to change the motion. It's its mass and velocity that determines how hard it is to stop it. Momentum is a vector. What's a vector? It's a measurement that carries on fire this morning. Displacement is an example of a vector, yeah. It has magnitude and direction. Magnitude and direction, as opposed to a scalar, which has just magnitude, right? So we can say displacement, Carrie, would be an example of a vector because we talk about displacement 300 kilometers north. It has magnitude and direction, as opposed to distance, which is a scalar, where you'd say it's just 300 kilometers, right? magnitude and direction. And finally, the equation that we use to find momentum, the main equation that we use to find momentum, it's a lowercase p. That's not a capital P. Capital P would be power. Somebody asked me why the symbol for momentum is P. Why would it be P? Somebody asked me that question. I don't know. I don't know why it would be P, but it is. The symbol for momentum is a lowercase p. And you see that has a little vector sign over it, a little half arrow. Capital P would be power, lowercase p would be momentum. And the equation would, of course, be m times v. That's the definition, right? The product of mass and velocity. What are the units here? Well, let's look at the units that we use for mass first. Mass would be in kilograms. Velocity, not speed, velocity would be in, but take a stab at that. For some of you, it's been like a year since you've done physics, but you can remember the units we use for velocity, Nick? Good, meters per second. So what do you think the units for momentum would be? It's staring you right in the face, literally. Is your hand up? No? Q? Yes, kilograms, meters per second. Kilograms times meters per second. It's kind of an odd set of units, eh? Like we like to have nice, convenient units, nice, tidy units like joules or something like that. But for momentum, it is what it is. Kilograms times meters per second. Now, sometimes you got to do some conversions here, right? Sometimes you're given a mass in grams as opposed to kilograms. How do we do that conversion? Let's say we got, I don't know. I go home tonight. I go to the grocery store because I want to make tacos. I go to the store and I buy 454 grams of ground beef. By the way, 454 grams is 1 pound. That's why I picked that number. How many kilograms is that? How do you convert that to kilograms? Yep. Yeah, you divide it by 1,000. You know what? If you're anything like me, you get mixed up whether we multiply or divide. I usually remember the conversion factor. It's 1,000. Grams to kilograms is 1,000. Multiply or divide. What do I do sometimes? Sometimes I remember. What do I do sometimes? Guess. I guess. If I guess, though, guessing's okay. Guessing is okay. It's underrated. Guessing is okay. But what do you got to do when you guess something? Check it. Check your guess, right? Check your guess. Let's say I went to the grocery store and I wanted 454 grams of ground beef, and for whatever reason, I wanted to convert that to kilograms, and I decided that I couldn't remember whether it was multiply or divide by 1,000. I guessed it was multiplied by 1,000. What do I end up getting here? 454,000 kilograms of dead cow. Does that make sense? That's a lot of cows, 454,000 kilograms. Clearly, I guessed wrong. Clearly, whoever said it, I think it was you, yeah, it was divide by 1,000, not multiply by 1,000. You know what? You'll do these so many times that you'll probably remember whether it's multiply or divide, but always check just to make sure. Check to see if it makes sense. Does my answer make sense? Okay, this one does. 0.454 kilograms. What about this? A lot of times we got to convert kilometers per hour to meters per second. Let's say we got 90 kilometers per hour. Actually, let's make it 100. The math is easier. 100 kilometers per hour. Convert that to meters per second. There's a long way and a short way. Well, I'll show you the long way, but then I'll give you the shortcut if you haven't seen that. 100 kilometers per hour is the same as 100,000 meters, right? Convert kilometers to meters, multiplied by 1,000. And there's 3,600 seconds in an hour. So 100,000 meters in 100 kilometers, 3,600 seconds in 1 hour. That gives me 27.7. What's the shortcut? Nick? Yeah, you divide by 3.6. When you do that, lo and behold, you get 27.7 meters per second. What if you forget whether it's multiply or divide, Nick? What if you remember, oh, it's 3.6. I remember that, but I always forget whether it's multiply or divide by 3.6. What if you multiply that by 3.6? What do we end up getting? 360 meters per second? Is that reasonable? Keep in mind that a football field is about 100 meters long. Not exactly, but close to 100 meters long. This would be 3.5 football fields. You're traveling down the highway at 100 kilometers per hour. You're driving 3.5 football fields in 1 second. That's about 20 meters per second faster than the speed of sound. So you're going almost Mach 1.1. Does that make sense? It's not going to be divide, right? It's going to be multiply. So again, it's okay to guess, but always check that guess just to make sure. Good? All right. Good. Let's do an example here. This is, by the way, in page 451 of your textbook that lots of you don't have yet. But remember, download a copy of it tonight or go to the library and pick up a hard copy of it. It says a 180 kilogram bumper car carrying a 70 kilogram driver has a constant velocity of 3 meters per second to the east. What's the momentum of the car driver system? I don't really care about this. We need to draw that. What's the momentum of the car driver system? What do we got here? Well, in Physics 20 and in Science 10, first thing we tend to do is just go straight to givens. Givens are important. They're very, very important. But they're not everything. It's more important, especially as we get to more complex things. This isn't so complex, but as we get to more complex things in Physics 30, it's more important to recognize what do we got? What do we have? Not what are my givens, not what are the numbers that I have written down in front of me, but what do we have in this question? Like what's the context of this question? What are they really looking for in this question? What am I going to do in this question? Look, clearly it's a momentum question, right? It's a momentum question. And since we've only got one equation for momentum, we know which one we're going to use. P is equal to m times v. Go through that process. It's not incredibly useful at this point because there's only one equation we've learned. But as we go further on, it's useful not just to look at givens, but to look at context. What's going on in this question? All right, let's write down a couple givens. My mass here would be what? 180 or 70? I want to find the momentum of the car driver system. Yep. Yeah, it's both of them. So it's going to be 250 kilograms. My velocity is 3 meters per second to the east. And I want to find the momentum. So look at this. Pretty straightforward here. We end up getting, what is that going to be? 7.5 times 10 to the 2 significant figures. Units. Kilograms, meters per second. Good? Wow, who said Physics 30 was hard, right? This is easy. This is easier than Physics 20, for heaven's sake. Nick asked a really good question. Says, do we have to put the direction? By rights, we should, yes. By rights, we should have at the beginning of the question said east is positive, and therefore we get a final answer that's positive 7.5. That's to the east. Like, strictly speaking, Nick, we absolutely should. But I'll tell you what's going to happen a lot. In Physics 30, we've gone through Physics 20 already. We've dealt with direction a lot in Physics 20. We deal with it a lot in Physics 30 as well. But in Physics 30, what tends to happen is that you internalize the direction. So we're kind of internally defining east as positive. So when we get the answer as positive, we know it's to the east without having written that down at the beginning of the question. Again, strictly speaking, we should write it down still. Okay? But in the end, if we get to the end and we know what direction it means, okay, that's what we end up doing a lot of the time. All right. Here's your first homework assignment for the year. And it's only 2 questions. And you got, well, maybe 2 or 3 minutes to do it here. Page 451, questions 1 and 2. We're not going to worry about drawing the momentum vector here. I just want you to calculate the momentum in question 1A and then calculate the velocity of the sled in question 2. That's it.